Hi, my name is Aniruddha Pal and today I am going to talk about my final project ImagineDim, which is a deep learning approach to estimate extensive properties such as weight and volume data from natural language. So what is the motivation behind this research? We know that humans have an imaginary sense of size in their language. So for example, if someone says a fox is similar kind of animal as a dog, without even seeing one in real life, we can estimate the size of a fox. And often, we use this imagination to plan our tasks related to various unseen objects. So now the question is, can we infer these extensive properties of objects from natural language? If we can, it can help various AI agents to search and do motion planning for unseen objects much more intelligently as seen in this research. Other researchers have also tried to find the answer. In the first research, they have tried to develop an unsupervised method to capture quantitative information from a large language corpus by searching physical quantities co-occurring within a specific window of the other nouns, adjectives, and events. And from that data, they created a distribution over quantities. It is a straightforward way to collect many extensive properties, but prone to noise and various biases. In the right-hand side, the researchers used linear probing on different language models to predict scalar magnitude. They have created a distribution around that data and concluded a strong relationship between scalar information and language models. However, this method is not particularly good at capturing raw numbers for each scale. So my goal is to overcome the limitations of these previous works and infer both the relative relationship between objects and estimate their physical attributes in numeric form according to real-world scale. So now let's talk about the data. For training and evaluating the model, the ShapeNet dataset is used. This dataset contains a large number of annotated data for various objects. The noise in the names are removed with NLP techniques and only English nouns are kept. But the thing is, in this dataset, no correlation is present between various objects, which is necessary to estimate attributes about an unseen object from the data of seen objects. To establish the relationship, I have used word embedding, more specifically Google's pre-trained word-to-vec model. At first glance, yes, word embedding has relationship between similar objects, but this relationship is not based on their extensive properties, rather on semantic properties. So how can we try to make a connection between unrelated semantic similarities with their extensive properties? The answer is a fully connected deep neural network. In this model, a fully connected deep neural network is trained to estimate extensive properties from the word embedding of the object. But a deep neural network can overfit any data and spit out values, which does not necessarily mean we have accomplished our goal. So the key questions are, is it learning or memorizing? How good is the prediction? And can it capture relative relationship of physical properties? To find the answer to the first question, I have split the data between the training and validation set and observed that during training time, loss for both training and validation set decreased simultaneously after each epoch. This confirms that it is possible to associate physical properties with the embedding vector, and a neural network model can learn to generalize the embedding space with respect to these properties. So it is not just memorizing the training data. So how about the quality of the prediction? Here we can see some random spike of error not only in the test data but also in training data, which is a predictable behavior as we are trying to generalize a large distribution of the word embedding space. So my conclusion is that though the prediction seems reasonable for a large number of objects, high error variance can make this model unsuitable for tasks requiring precise estimation. Now let's talk about the relative relationship. In real life, we don't always need the accurate physical property of an object to do various tasks. relative accuracy is good enough. For example, if we can lift a dog and we know a cat is lighter than a dog, implying these two data, we can confidently tell that we have the ability to lift a cat too. Likewise, if we can fit a book in a bag, we can also fit a pen in that bag. That's why the ability to capture this relative accuracy is also measured for this prediction model. This measurement aims to determine, for example, if tiger weighs less than elephant in real life, whether the model's weight prediction of tiger is also less than the prediction of elephant. Here we can see the relative accuracy for this model is 77% for weight data and 75% for volume data. So the conclusion from this measurement is that the model can preserve a significant amount of relative accuracy, which can certainly be useful in various situations. So what we have achieved through this research? I would say this work creates a baseline for associating annotated extensive properties of objects with word embedding to estimate the physical properties of unseen entities. It shows a promising development and establishes the viability of capturing physical properties in language models with annotated data. I want to share one limitation of this model with the audience. This model is highly sensitive towards hyperparameters. Increasing or decreasing the learning rate or changing the number and size of hidden layer can drastically affect the final outcome. One possible reason can be the sparsity of input-output space, but this is needed to be investigated more in future research. And further research should be done with other kinds of datasets and more sophisticated architecture to improve upon the work on this research. For example, one key research area can be using visual data along with language embedding. Though the word embedding can effectively predict physical characteristics like weight or volume if trained with annotated data, it still does not have any direct physical entity encoded in its vector space representation. So I believe introducing image data might improve the result significantly, which has a direct correlation with the physical attributes. And one advantage of that is we can then use attention or a convolutional like sophisticated model for better prediction in future research, which seems ineffective in the current input-output scenario. Finally, I invite you all to go through the detailed report to find out various intricate details about the training process, and thanks for listening.